So hi everyone, my name is Josh, and today I'll be talking about sort of multidimensional radio transfer calculations of the D6 scenario. Um, yes, like Vinton, I work in Professor Stewart's Sims group, and we take these hydrodynamical models that are developed by our collaborators at NPI and HITS in Heidelberg, who they perform the subsequent in-spiral explosions of these white dwarf mergers. They perform the nucleosynthesis post-processing, and then we perform the radiative transfer across various different regimes and compare to observations. And the specific explosion models I'll be talking about today are the D6, and we can think of these as lying somewhere between a classic substratospheric helium accretion model and that of a violent merger. And sometimes they're called D6 models, and they are called D6 models, but sometimes they're called gentle mergers. And this is sort of misleading because we can often think of these as the most violent type of merger possible because they occur at the earliest stage of the merger. The specific models that I'll be talking about today are those generated by Rudiger Packmore in his 2021 paper, with the first model being the one explosion scenario. And what we get is we get this roof-loop overflow, we get in-spiral of helium, dynamical instabilities leading to a double detonation, and the secondary white dwarf will survive the simulation. It will escape, and it will be escaping with quite a high velocity, around 1,000 kilometers a second, and it will be polluted with the elements synthesized in the primary explosion. And this sort of what leads to these theoretical predictions of these fast-moving white dwarfs. And the likes of Ken Shen has searched for these in Gaia data releases, and we have found some of these hypervelocity white dwarfs, but there is still a somewhat about an order of magnitude mismatch between the expected rates of these and the numbers that we see. One possible explanation is the secondary also may be detonating. So Rudiger has restarted these explosion simulations. We get this in-spiral of helium, a double detonation on the primary, and then we get the same converging shock waves also detonating the secondary white dwarf. And whenever these models were generated, this was back in 2021, and more recent simulations have been able to achieve self-consistent detonations and also crucially reduce the amount of helium on the surfaces of these white dwarfs. And while initially you may be thinking that the impact of the helium shell and the thickness of it will primarily influence photospheric phase results, the overall compression caused by the overall compression caused by the total amount of helium also has impacts for the nebular phase. The overall abundances and densities can be seen for the one explosion model on the top left and top right, and the two explosion model on the bottom panel. And what we can see is that the outer ejecta is for both scenarios is quite aspherical, but they're quite comparable to one another. And it's only deep within the center of the models that you see this inner bubble region left behind by the secondary's detonation. And what's something that's really crucial to understand is that the delay time between the secondary exploding and the primary exploding is only about 3 seconds. And it's crucial that more recent simulations understand that the timing of that secondary detonation. The photospheric phase simulations for this are quite interesting. And what we've got here on the y-axis is the flux compared to and then the wavelength. And we've got 3D cases and 1D cases. And the node helium models have had that helium shell detonation artificially removed. And what you can see is that no matter if you perform a 1D calculation or a 3D calculation, the models look really, really similar at early times. And once you remove the helium, you can see here out that towards the UV, you get this overall increase in flux, which is closer to matching that of normal Type Ia supernovae. And thus, again, it is crucial for more recent simulations of this class of model to reduce the amount of helium. So the remainder of the talk, I would like to talk about the nebular phase. And what we can see here is that we've got a super SN 2021 AFX, and that was quite special because it has been observed by JWST. So initially here we have the 1D1 explosion model, and what we can see is that it is broadly consistent with previous double detonation models, where the model struggles to reproduce some of the optical iron features between 4,000 and 6,000 angstroms. Whenever we look at the explosion model, what is immediately really apparent is that the strength of that iron 3 feature is quite weak compared to observations. And it's also notable is that we get a contribution, oxygen 1 contributing at around 6,000 angstroms, and we also obtain a small amount of calcium 2 at 7,000 angstroms. Looking to the 3D1 explosion scenario, and we obtain spectra that is broadly quite similar. We get some small changes in the flux at around 7,000 angstroms, but overall, the 3D effects on the spherically average spectra are quite, you can't really see a large difference between the 1D and 3D case for the angle average. Looking at the 3D2 explosion model, what we can see is that this initial central iron 3 peak more than doubles in its luminosity, bringing it much, much further in line with observations. We see that there is the total amount of flux here, which the models predicts to be, in the 2 explosion scenario, a mix of argon 3 and calcium 2. Overall, we get a reduction in that flux, and we also get an increased contribution of calcium 2. Again, is very comparable to the 1D1 explosion model. And then finally, if we look to the 3D2 explosion case, we see that there are more detectable differences due to 3D in the near infrared. And one thing I want to mention is that this feature at 3.5 microns is noticeably absent from the simulation. And this is because it has been attributed to a calcium 4, which was not in our composition files, but going forward, future simulations will investigate this. The near infrared, or sorry, the mid to far infrared produce quite a different set of characteristic observables. And what we can see is that JWST will be really useful at investigating different morphologies and line shifts. But because we're now looking at 3D simulations, we can look at various different viewing angles. And what we can see is that the 1 explosion scenario doesn't predict a large amount of viewing angle variation in the optical. Whereas when you compare that to the 2 explosion scenario, you can see we get a large increase in the viewing angle variation for different lines of sight. And that can be contributed to the different density structure of that model. But what's really interesting and is kind of the aim of my further investigation of these models is to build up these detailed profiles of how the velocity changes at different times as we move across the merger plane. And what is really interesting is that there are key detectable differences in the nebular phase, far more than the photospheric phase, for these 2 types of models. And because we've now performed 3D photospheric phase calculations and 3D nebular phase calculations, we're able to start testing new hypotheses, such as investigating how silicon 2 velocities correspond to the iron velocities in the nebular phase. But I will just leave up my conclusions, and I'm happy to take any questions.